Hello, this is Peter, and today's video is to use Explicit Dynamics to crush down a structure with a high-speed block coming down at 20 meters per second. So this was a problem a Redditor asked me to look at, and I'm going to spend a little time looking at their first attempt and this model that's successfully running. So stand by. The Redditor sent me this model, which has this internal structure. It's all solid bodies with slightly thicker walls called wings, and this is an aluminum plate defined with plasticity in a bilinear hardening model. With just elasticity on the top and bottom plates to fixed plate on the bottom and moving plate on the top. There is bonded contact to hold the wings and the inner and outer structures together, and then some frictional contacts, self-contact here between 6 bodies, and then top and bottom contacts with the crushing plates. We're going to replace all that with simply the body interaction feature of Explicit Dynamics. If we take a quick look at the mesh, there's only one element across the thickness of the solids, and that is insufficient for this kind of model. You would want at least 4 elements through the thickness of each wall. And in the analysis settings, there's an end time of 40 milliseconds, but if you divide 150 millimeters, which is the length of this structure, by 20,000 millimeters per second of velocity, you find that the structure collapses to 0 in 7.5 milliseconds. So a 40 millisecond end time is not useful, and we're going to update that. So let me first suggest that we're going to do a model where we replace these thin sections with shell elements so that we can mesh them efficiently, and that's what I'm going to show in this video. So let me duplicate the model, and I did it once here, but I'm doing it again for the demo to show how to open up this model in SpaceClaim and create that shell surface models at the mid-surface to replace the ones that were solids. So here comes the geometry. It's from an IGES file. It came in as surfaces. So we go to the repair tab and stitch it together, and we find we now have a fewer number of solids. The top and bottom are going to remain blocks, but these ones are going to be replaced by mid-surfaces, which is on the Prepare tab, mid-surface, and that's to pick 2 items, and it automatically turns them into mid-surface bodies, which retain their knowledge of the thickness, so you don't have to type the thickness in. That gets sent over with the model. And we're going to check we in fact got lucky that the software was smart enough to extend these to the midline of the outer portion. So that is perfect. Suppressed for physics all the solids we didn't want. And the last thing is we don't want any bonded contacts, so we're going over to the Workbench tab, click the Share button so that there will be shared nodes that hold the wings to the inner and outer structure. So we are all done in space claim, and we can work on it in mechanical now. Okay, the geometry is finished being read in, and we'll just fix up all of the items that have problems, which is mostly material assignments. These are the blocks, and they are the 25 kilogram plate material, and the mid surfaces, which each have their own thickness, but lack the material that they were assigned, which is the aluminum. So our geometry is good. We're going to delete all the contacts that were there. We don't need any of those, so we just delete. And we're going to use body interaction as the only contact that we need. On the mesh, we don't need any of this. We're going to just use a default element size of 4 millimeters, and we're going to also not need that displacement, but let's go ahead and mesh first, generate, and zoom in. Here's our structure. The fixed support, we'll just do that on a face. We're going to select this face here, and the velocity is the body. So we'll pick a body, and that whole body has got the downward velocity. As I mentioned, 40 milliseconds is too long, so we're going to do 5 milliseconds, because we don't want to crush it to 0 thickness. Another important setting is the output control defaults to 20 frames, and I'm going to ask for 200 frames in those 5 milliseconds. The other item I put in, which I'm not sure if it's required, but I want to have this body get a initial velocity. It's not a named selection, it's a piece of geometry. One body, and 20,000 millimeters per second in that direction. Downward, apply. So with that, we're going to solve, and let's look at the solution information. The original model seemed to want to take more than an hour. This one's going to take a few minutes, but I'll halt this and go over to the other model. Here's our solved version, and what we see is back to the solution information. It did take 8 minutes to solve. Well, took total elapsed time, runtime 1 minute of runtime. I didn't time it, but anyway, the thing I added that wasn't there before was the energy probe, and the original model with solid elements had an energy error too large, but it did not have enough steps, and it was trying to crush it down to a negative volume here. So here what we see is the hourglass energy is very small, and that's an important feature, and the energy going into contacts is quite large, so self-contact energy, and plastic work. That's all the deformation in the walls. So that is where we're at. And the other item I added was the force reaction, so that fixed support. It spikes up a little bit because these walls are perfectly straight, and then once it starts buckling, it comes down to reasonable values, and that could be, the spikes could be reduced by inserting some pre-buckled shape into the geometry before we start the simulation. So instead of all these walls being perfectly flat and straight, we could inject some mode shape from a buckling analysis to pre-buckle the shape, and that would lead to a more smooth buckling behavior. So I think that's a good summary of what I did to get this to run, and hope this is helpful.